Alright students, let's look at this question here, which is on complex numbers. So it was taken from the year 2017 CJC paper 2 question 4. Now you're given that the complex numbers z and w satisfy this simultaneous equation, and we are told to just solve this. Now what I'll usually tell students is simultaneous equation is similar with what you learn in secondary school, instead that now it's just in complex numbers. So there are some additional tricks to do. So this case here, I'm going to use substitution. I'm going to make z the subject. I'm going to substitute to one another, right? So I'm going to make z a subject here. So from the first expression here, a, let me just write it down nicely. Here, what we get is a is equals to z equals to 10 minus w conjugate minus 5i. Okay. So from here, what I get is z, make z a subject, and we're going to sub into the second one. So sub 1 into the second equation, z plus 18 plus I. Okay, then what we're going to do is actually just replace this modulus w square is equals to 10 minus w conjugate minus 5i plus 18 plus I. Okay, then we're going to do here is just add everything up. This is 28, 28, yeah. 28 minus w conjugate minus 4i is w modulus square. Now, so now we have everything in terms of w. So w conjugate and w. So just let w equals to a plus bi, complex number where a and b are real values. Okay, this is important. Essentially, you need this to be real value here. Then what we're going to do is actually just replace it in modulus a plus bi square equals to 28 minus. So this case here, so this will imply that w conjugate is a minus bi. Okay, so this is a minus bi minus 4i. Then just expand this, which is a square plus b square. Let's replace this. A square plus b square equals to 28 minus a plus bi minus 4i. So this will just be a square plus b square equals to 28 minus a plus b minus 4i. Okay, so now with this, what we can do is actually compare the real and the coefficient, the imaginary, because this part here, you can equate to both of them. So by comparing, once you have all these terms here in real plus imaginary, by comparing the real and imaginary parts. Okay, I'll just take note. This one here is real. This a square plus, so this is 0i. So b minus 4 is actually equal to 0. And after which, you have got the other one, which is 28 minus a is equals to a square plus b square. So it's pretty okay. So b minus 4 equals to 0. So this is b equals to 4. Then we have a square plus b square equals to 28 minus a. So this is a square plus 4 square equals to 28 minus a, because b is 4. So this case, a square plus a equals to 16 minus 28. Let's key this in. 16 minus 28, that will give us minus 12. Oh, this is pretty nice. So then we're going to get 1 minus 12. This is a equals to 3 or negative 4. Okay, so there's our b there. So we get w. Yeah, w has got two expression here. So it makes sense because b is 4, right? So w is actually just a plus bi, so it's 3 plus 4i or minus 4 plus 4i. Okay, remember that w is a plus bi just now, this one. So just replace it in. So we have two possible answers here, after which we're going to just use z equals to w conjugate. So z, this corresponding here, this z will be using this formula, 10 minus W conjugate. 10 minus W conjugate will be minus 4i. Okay, maybe this conjugate here. Minus 5i. Okay, after which this will follow the same. It's 10 minus 4 plus 4i. W conjugate minus 5i. So just key in this. 10 minus 3 minus 4i. 5i. This will just be 7 plus 4 minus 1 minus i. Then this will just be 10 minus 4 minus 4i conjugate. 10, 14. This is 14 plus 4 minus I. Alright, so there you go. So hence we have the solutions. The two solutions are actually 3 plus 4i z equals to 7 minus I semicolon. This is one set of solution here. And then we have got another one which is w equals to minus 4 plus 4i. And this will be z equals to 14 minus I. Okay, so that's how I do this question here proficiently. If you have any questions, please let me know. It's a pretty interesting one. And let's look at how we can do the next one. So let's get part B is given at 2 plus I is the root of this equation here. Find the second root of the equation in Cartesian form. Showing your answer clearly. Now there are a few ways. I think I'll just do the easier B, I. So we know that the root of the equation is actually 2 plus I. Okay, let the other root be alpha. Okay, we're just going to solve alpha. So the other root will be alpha. So hence, we know that z minus 1 root, if this is 1 root here, and the other linear root factor will be z minus alpha. Okay, this will give us z square minus 5z plus 7i. I think this comparing the coefficient will be the easiest. Okay, so if this is a root, obviously z minus this will be a factor. Then this another would be alpha. Then you just compare, right? So this case here, you can expand actually. You just compare. But okay, I'm just gonna slowly do it. Z. Okay, actually you can just compare this with this one. Okay, so compare the constant. So by comparing the constant here, by comparing the constants, you just take 2 plus I alpha is equals to 7 plus I. This case here, alpha is equals to 7 plus I divided by 2 plus I. Remember, you can just use calculator. Now, a lot of times students forgotten that they can use calculator. The question did not say that you can't use GC, I assume. Okay, so if they do not use, you don't need to just go and calculate it out, but you can just use your calculator here. So when you use your calculator, this will just be 7 plus I over 2i. 7 plus I over 2 plus I. That will be 3 minus I. Okay, this is 3. Hence other root. Minus I. Okay, that's how I do this part here. Then we're going to look at part 2, hence find the root of this equation. This is pretty interesting. This part here, what you need to do is actually just look at the constant here, this constant here. So I think this is the main thing we need to know. So you change the constant as far as what is different here is basically the constant, right? So how do you get this constant to be the same? So you can just use calculator quickly. So 7 minus I. Okay, usually there's a multiple here, then divide by 7 plus I. It's actually, oh, is it 7 minus I? 7 minus 1. Sorry, 7 minus 1. 7 minus 1. 7 plus 7i minus 1. Sorry, 7i minus 1 7i minus 1 divided by 7 plus I. Okay, great. So this is what? So you realize it's just an I. So you can actually see this quickly that you just need to multiply by I to get this. Okay, actually you don't really use calculator, but you can just use so there are many ways. So I'm gonna just try to change this equation here to this equation here to this part here. So the first thing is actually z square minus 5z plus 7 plus I. Actually what I think maybe we can just use minus IW square. This works as well. So I could change this to this as well. So I think either way is fine. So I'm just moving here backwards. So here you can see that 7i, to get 7i to 7, so you just multiply by minus I here. Okay, so both sides here, what we're going to do is actually just multiply by minus I. So just anchor using the constant first. So this will be I square, W square minus 5i, W minus 7i square plus I. Okay, so you multiply both sides by negative I. So negative I times negative I will be I square. So this part here we get is I W square minus 5iw plus 7 plus I equals 0. So this is similar to what we got here. Okay, so you see this is minus 5z. So there's a minus 5 here, so which is quite convenient. So if you group them, iw square minus 5iw plus 7 plus I, you know that you substitute z equals to iw. Okay, so there you go. If you were to sub z as iw, you get this. You just group that, this iw. So in other words, if z from the previous part is equals to 2 plus I and alpha, so this 2 plus I, alpha would be 3 minus I, so this would just be iw. So w will be equals to 2 plus I divided by I, or 3 minus I divided by I. So I should just put this as or. Then king calculator, okay, this one you could just king calculator, same thing, 2 plus I divided by I, 1 minus 2I, or we just put, what is it, 3 minus I, is it? 3 minus I divided by I minus 1 minus 3I. Yep. So that's how I do this question proficiently. Let's look at the last part, which is part C. Let's look at C part 1, C part I. So essentially, you're given that z is equal to minus a plus a. Now you realize that actually the ratio of the imaginary to real is actually 1 to 1. So it means argument. Now remember there are only two ratios, 1 to root 3 or root 3 to 1. As long as the length in terms of this ratio, you can actually find the exact argument. Okay, so this one just take note of it. Now then after which a is a positive real, so we don't need to worry. We know that which quadrant this complex number is in. So it's given that this w is this, express w in this form. Okay, great. I'm just going to find out what is the argument for z first. Okay, before I even start. So c. So z is equals to minus a plus ai. What we're going to do is actually just draw this out. So minus a plus ai is actually in the second quadrant, right? This part is minus a. This is a. Then you go through this part. So this part here will be pi over 4. So this is very quickly, this is 3 quarter pi. So you get like 3 quarter pi here. Okay, so meaning to say, argument of z is just 3 quarter pi. Okay, I know pi over 4 is because this length and this length are the same, which is 45 degrees, right? The length is just 45 degrees, so 45 degrees is pi over 4, then after which we just take 180 minus 45, that will be 3 quarter over 4, 3 quarter pi. Now then after which what we're going to do is actually just find w. So we need W is equals to, okay, we find the modulus first. Modulus Z is quite straightforward. It's just A square plus A square. So this case here, what we get is actually just square root 2A square, which in turn gives us root 2A. Right. So this case is done. Then W would be minus root 2 over Z4 Z conjugate. So if you want that in that form, what we need is a modulus of W first. Modulus W will be modulus of the whole thing. Root 2, maybe I write it nicely. About 4 is Z conjugate over Z to the power 4. Alright, then this case here, what we get is when you mod the negative, of course, is positive. So this is 2 modulus Z conjugate is still modulus Z. This is modulus Z4. So these two can cancel because modulus Z conjugate is equals to modulus Z. Alright, so this will be root 2 over mod Z to the power 3. This is, just take note now. Modulus conjugate, so these two can cancel away. Okay, left with a 3 below. Maybe I just do this, not skip step here. Okay, you can skip here, of course. Cancel away. Maybe root 2 over mod Z cube, which is actually root 2 over mod Z, which is actually A cube. Okay, so root 2, this is A cube, so root 2, this is root 2 times root 2 times root 2, and this is A cube. This root 2 will cancel away. And what we left here is 1, 1. This is 2, so it's 2. This is 1 over 2A cube. Okay, there you go. So we got the modulus. Then after which we need to find the argument. So the argument, just remember, when you find argument of W, just argument of minus root 2 Z conjugate over Z to the power 4. This will just be argument W root 2 Z conjugate minus argument Z to the power 4. It behaves like log is precisely the logarithmic, it's the same. Okay, so here, once you're done, what we're going to do is actually just break this apart. Argument of minus root 2 plus argument of Z conjugate minus 4 argument Z. This 4 can be brought down, right? So here's this. Now take note, argument negative real number is actually pi. Okay, because if you were to draw on a Argand diagram, negative number will be here. So this is pi. Alright, so you essentially look at that. So then after which, the other one, which is argument Z conjugate, is actually negative argument Z, which we already know as well. So this is the one which you need to take. This is pi, and this is argument Z. This is minus 4 argument Z. There you go. So once done, this will just be pi minus 5 argument Z. And we have argument Z just now, which is 3/4 pi. So pi minus 5 3/4 pi. Key in calculator. Okay, 1 minus 15 over 4. 1 minus, that will be negative 11 over 4. So obviously this is out of range, so I'm just at 2k pi. So at 2 will be negative 3 over 4 pi. And this is within the principal argument. Alright, so you just remember this. What you do is just 1 minus 5 times 3 over 4. It's plus 2. You get negative 3 over 4. Okay, so there you go. So hence W is actually 1 over 2a cube EI minus 3/4 4 pi. There you go. So that's how you do this question here proficiently. If you have any questions at all, please let us know. Keep practicing and I'll see you in the next question. Let's look at the last part. Find the two smallest positive value of numbers n such that r wn is equal to 0. So now that we have got w, so we need the real part of wn to be 0. Real part of wn to be 0 meaning wn to be 0 meaning wn is purely imaginary. Okay, because if this is 0, it means wn would just be equal to 0 plus ki. Okay, because the real part will be 0, so it's just purely imaginary. This is what you need to be able to tell. So from here, if wn is purely imaginary, meaning wn, the argument of wn will be pi over 2 plus k pi. Maybe I should use this one, should be like pi. So this case here, k, z. Now how do I know that? So on the Argand diagram, same thing. I would suggest just do this. So this is imaginary here, this is pi over 2. Okay. Any complex number here fall within on this axis here will be imaginary, pure imaginary. So you want it to just keep this, and also this, so you just plus k pi, because you just keep adding 180 to it, okay, so that you get the complex number on this axis here. So once done, this will be n argument w equals to pi over 2 plus k pi. Alright, n argument w. Okay, so what we need is the value of whole numbers. Argument w was minus 3 over 4 pi. So this is just minus 3/4 pi equals to pi divide. So this case here, n is equals to minus 4 over 3 half plus k. Okay, so this is it. So what do we need? Two smallest positive value whole number. You can use GC. If you don't use GC, you can also try and error. Actually, make this a common fraction would be good. Okay, so this will be minus 4 over 3, 1 plus 2k over 2. There you go. So you can see that actually n behaves like that. So if you want n to be the two smallest positive whole number, this can be a multiple of 3. So we can just key in and show you. So this case here, you only get minus 2, 3. Then we're going to put this 1 plus 2, 1 plus 2x. Second table. So you want it to be positive, of course. You have to make it positive. So it is here. So you want two smallest positive whole number values. So these are whole number values here. Here, these are 2 and 6. Okay. So this case here, what you do is essentially, this is n. And this over here is your, this is your k. This is your n. Now all these n values here will render the complex number wn to be purely imaginary. But there are only two which are these are whole number. Okay, here and here. So the two smallest, hence from GC, two smallest positive whole number n equals to 2 and 6. Okay, 2 and 6. So that's how I do this question here proficiently. If you have any questions at all, please let us know and I'll see you in the next question.